You hear about time travel and picture-flashing machines, yet the real surprises sit inside calm equations. Einstein's gravity lets space-time curve so deeply that a path can loop back to the very moment it began. Here's the key: a closed time-like curve, which simply means a route through the fabric of reality that returns a traveler to their own past without ever breaking the speed of light. Think of a hiking trail that circles a mountain and delivers you to your earlier footprints. We begin with time travel physics, a sober inventory of what the math allows and what nature likely forbids. You and I will weigh rotating universes, spinning cylinders, wormholes, and quantum loops against causality, which is the rule that causes must come before effects. Notice how even the vocabulary sounds gentle, yet the stakes are enormous. If closed time-like curves exist in the wild, then yesterday is not a memory. It is a reachable address with traffic rules and exit ramps. You deserve an early map before we descend into details. We will meet the Gödel universe, where the cosmos rotates. The Tipler cylinder, a dense object spinning so fast it drags time, and wormholes, space-time tunnels that need negative energy to stay open. A simple way to keep our footing is to define paradox early. A paradox here is not a riddle, but a self-knot in logic, such as trying to prevent your own existence by changing the past that produced you. Let's set your agency clearly. By the time we finish, you will be able to trace any time travel claim back to the physics that could support it, and you will spot the red flags without waiting for an expert to weigh in. Here's why the Gödel universe matters beyond its elegance. In that exact solution, global rotation tilts the light cones, the local envelopes of possible motion, until a patient traveler can follow a lawful path that returns to earlier times. If you like analogies, imagine a city where every street subtly leans the same way. Drive long enough without breaking any speed limit, and you reappear at a morning intersection you already crossed. The roads did the magic, you simply followed them. We immediately face the feasibility question you are probably asking. Our universe does not look globally rotated in the required way. So Gödel's path is a demonstration of permission in the equations, not a blueprint you and I could pave tomorrow. Quick thought before we go deeper. Tell me your city and your local time, because time feels different when you picture the sky from your own horizon. Hold that thought and meet frame dragging, the way spinning mass twirls nearby space-time, the way a whisk pulls batter. If you extend that idea to a nearly impossible extreme, you reach a thought experiment called a Tipler cylinder. You can picture it as a star-dense, needle-long object spinning so fiercely that nearby light cones tip enough for lawful loops into the past. It is not a fantasy of speed. It is a choreography of geometry tugged by rotation. We should be candid about the engineering. The cylinder would need improbable density, near perfect uniformity, and a length measured against cosmic scales. Even then, quantum effects and material strength would likely veto the build. Here's the key, and it sounds simple. A wormhole is a tunnel through space-time that, if stabilized, can connect not just distant places, but different moments, provided one mouth experiences a time shift relative to the other. You might have heard the phrase negative energy, which here just means an energy density lower than empty space, a curious feature that quantum fields can display in small amounts under special conditions. That unusual ingredient can hold a wormhole throat open. A simple way to feel the requirement is to press your palms together and imagine the vacuum between them turning into a small pressure debt. The tunnel wants to collapse like wet clay, so you need that debt to counter gravity's squeeze. We invite your skepticism, because skepticism protects wonder from wishful thinking. Known quantum effects can create short bursts of negative energy, but scaling them into a stable, human-sized tunnel would demand control we do not yet possess. Notice how our ledger is balanced. Equations say yes. Materials and quantum back reaction whisper, not so fast. And thermodynamics asks whether the whole construction would explode into radiation the instant a loop becomes possible. If you move one mouth at high speed or sit it in a strong gravitational field, its clock ticks differently than the other mouth's clock. Bring the two together again, and you have a bridge whose ends disagree about the date. Step through, and you step into else when. We should pause over the word causality, the everyday rule that events unfold in an order everyone can agree upon locally. Loops break that comfort because a careful traveler can deliver information to the past and reshape the very reasons they traveled at all. Here's a micro puzzle to settle your nerves. If you send a note back that says, "Do not send this note," must the universe turn to nonsense? Or will it arrange small accidents so the note is always sent, preserving consistency like a self-correcting story? Many researchers explore the self-consistency principle, which says only history-respecting events occur. The past you reach already includes your arrival, so you can nudge but never contradict. It is tidy, yet it trades freedom for coherence. We can express that trade with an everyday analogy. You can improvise a melody around a fixed bass line, but you cannot play a chord that erases the bass. The loop's earlier measures already contain the notes you are about to add. Here's why that question lands so sharply. If every attempt to defy the past slips on a banana peel placed by physics, then agency becomes a set of narrow corridors where your intentions survive, but your illusions of control politely vanish. We can chart another path many people prefer. In a many worlds reading, changing the past simply places you in a neighboring branch with a different history. Your original timeline remains intact, and paradox dissolves into divergence. You might picture a library where each decision is a new shelf. Walk back with knowledge from your shelf and step onto a nearby one. You have edited nothing on the original shelf, yet the story you now live contains your interference. Notice how that option moves the controversy. Instead of asking whether paradox is allowed, we ask what counts as the same world, and whether probability flows cleanly when you copy the book of reality across shelves. We keep this grounded by staying with calculable claims. Some models of quantum information show that loops can be made consistent without contradiction, but the price is a kind of noise that smears sharp choices into fuzzy averages. If you have ever averaged a few blurry photos into one clearer image, you know the feeling. Detail returns, but individuality softens. Time loops can perform a similar compromise, stabilizing cause and effect by accepting a bit of statistical haze. Let's place a friendly warning flag before we climb higher. Exotic setups that permit loops often hover on the edge of instability, where a single photon racing around the loop can trigger runaway amplification and scorch the experiment. A simple way to imagine that problem is with microphones and speakers that feed into each other. Turn the dial a little too far and the system howls. Loops in space-time can behave similarly when energy chases its own tail. Here's the key move that keeps theorists curious. Down near the Planck scale, which is the unimaginably small realm where quantum gravity becomes loud, time may already be fuzzy, and microscopic loops could appear and vanish like bubbles in a simmering sauce. We make that idea practical by asking what information can do. If quantum states refuse to be copied perfectly and every measurement disturbs the system, then tiny loops might smear information just enough to keep causality safe on large scales. You can think of it as a security watermark woven through every event. Try to stamp a contradiction into the past, and the watermark shows up as noise, quietly absorbing the mischief and returning a history that still reads cleanly. We are careful with the word proof here. Elegant hints live in equations, But a full theory of quantum gravity is still under construction, so we treat loop-friendly sketches as promising maps, not final territory. If you enjoy bridges between ideas, the holographic principle supplies an unexpected one. It says the information inside a region can be encoded on the boundary. So, reshaping boundary data sometimes looks from the inside, like edits to the storyline of time. We will keep this down to earth with a kitchen picture. Change the recipe written on the outside of the jar, and the flavor you taste inside changes, even though you never touch the stew directly. Boundaries can be tyrants in physics. With that in mind, return to wormholes and ask a workmanlike question. Could a civilization collect and arrange enough negative energy pulses to coax a tunnel into stubborn stability for more than a flicker? You and I run into two walls immediately. First, known quantum inequalities cap how much negative energy can sit in one place for one stretch of time, and second, the tunnel warms up under stress, threatening to flood itself with destructive radiation. We can keep your curiosity alive without killing the wonder. The constraints don't say never. They say, go carefully. If nature allows tunnels at all, they're likely rare, small, and stabilized by conditions we barely understand. Here's the key philosophical move many physicists adopt. Instead of hunting devices, we ask whether nature hides a general guardrail called chronology protection, a tendency for the laws to conspire so that macroscopic time travel never quite gets started. If you crave an everyday analogy, think about how traffic lights across a city can be timed to discourage speeding. You can floor the pedal between two intersections, but the next light will likely catch you. The system is tuned to preserve order. We take that hint and test it against each candidate loop. Rotating universes fail on observation. Cylinders fail on materials and quantum feedback. Wormholes face energy bookkeeping and thermal tantrums. Quantum loops seem to blur rather than break causality. Notice how this tally preserves wonder instead of destroying it. The universe is not boring, it is watchful, letting imagination range across the landscape while quietly pruning paths that would erase the very reasons events make sense. If you enjoy computation, here is a sideways insight. Hypothetical computers given access to perfect time loops could solve some problems, alarmingly fast. But realistic loop rules inject noise that collapses that advantage, again pointing to a protection pattern. We can translate that into plain speech. When a shortcut threatens to trivialize the puzzle, physics adds a tax, a sprinkle of randomness or a stability limit. So, answers stay meaningful and causes still earn their effects. A simple way to explore this at home is to become a causality detective. Whenever you see a time travel story, ask 3 questions. What geometry makes the loop? What energy feeds it? And what stops runaway feedback from tearing it apart? We return, briefly, to the self-consistency principle and show how it rescues narratives without flattening them. You can deliver information to your earlier self that helps, but only if that help was already part of the route that took you here. You might feel that as a paradox of responsibility. You get to become the author of the very letter that inspired you, yet you can never choose to burn the letter, because there you stand, letter in hand, remembering the burn that never was. Here's the answer that surprises many viewers. In a consistency-respecting loop, the firmest machine is not metal, but memory. You protect causality by doing exactly what already happened, and freedom becomes a promise you willingly uphold. We can honor how human that feels. You already live inside soft loops when you keep traditions, replay rituals, or revisit a conversation with wiser words. Nothing breaks because the new act harmonizes with the history that shaped you. Let's shore up one last engineering corner: energy conditions. which are rules of thumb for how matter and pressure behave under gravity. They are not laws etched in stone, yet they guide us by saying which curves of space-time tend to be physically reasonable. If you picture a bedsheet held at the corners, energy conditions tell you which pinches and pulls will sag the cloth without ripping it. Violating those guides to make a loop-sized tunnel may require stresses that ordinary matter cannot survive. We have been careful to respect your attention, so here is a compact checklist you can carry. Geometry permission, exotic energy budget, stability under feedback, and a causality guardrail that refuses to vanish. If any one fails, the time machine collapses. If this tour clarified the difference between math permission and nature's guardrails, consider liking and subscribing so more curious minds can travel these roads with us. We should also let wonder breathe for a moment. Even when the big doors seem closed, small fluctuations near the quantum grain of space-time crackle with possibility. The way frost patterns grow on glass with intricate logic. You can keep your imagination honest by anchoring it to measurable questions. What signals would betray a natural wormhole? How could an observatory notice a time-shifted echo? And which noise patterns would confirm a consistency-preserving loop? Hold that thought. We are nearly ready for our largest feeling today. Before we arrive, recall that awe lives where the unknown is framed by understanding. That is how you stay brave without drifting into fantasy. Time does not flow, structure does. The river you feel is your mind crossing a fixed landscape whose valleys are causes and whose cliffs are effects, and every lawful path through that terrain is already drawn, whether or not you ever walk it. You stand on a ridge in that landscape now, with yesterday to one side and tomorrow to the other. The miracle is not that the map might include a loop, but that meaning survives even when the trail briefly doubles back on itself. We can state the verdict with kindness. The equations of relativity allow loops under special geometries, quantum fields offer strange energy in careful doses, and yet nature surrounds the most extravagant roots with thorny hedges that protect coherence. You are not shut out of wonder by that protection. You are invited into a deeper one. A universe that guards causality is a universe where explanation is possible, where your choices matter because consequences do not evaporate when you stare too hard. Here's the practical payoff you can carry into every science story. Ask what bends the light cones, who pays the energy bill, what stabilizes the path, and how information avoids contradiction. Then enjoy the tale with both delight and discernment. If you ever feel that this restraint dims the romance, remember music again. The rules of harmony do not strangle beauty. They make it legible. And within them, the surprise of a new chord can still bloom into goosebumps. We close where we began with a friendly map. Rotations, cylinders, and tunnels mark the permissions. Feedback, energy limits, and quantum noise draw the boundaries. Together they sketch a cosmos that prefers stories that can be told twice the same way. You now have the detective's kit, and you can use it gently on your favorite narratives. When a plot hands you a loop, you can smile, tip your hat to the equations that inspired it, and decide how much realism you wish to demand. Let's keep the invitation open, because good science is a long conversation. If new observations ever nudge one of these hedges aside, you and I will be ready with sharper questions and a renewed appetite for the possible.